Hello everybody, and welcome to the normal distributions and their relationships to the empirical rule. Keep in mind here that we're not actually doing any particular problems in this video. We're going to be looking at concepts that you should have between the chapter on dispersions going up to the final exam. And this is going to link some of these old concepts back together. So more than being a practice video, this is a, oh crap, I have to remember this kind of video. So, as a quick refresher, one of the first things that you should know is that you started out with a bell-shaped curve way back in the beginning, with a center being the mean. And according to the empirical rule, if you went up and down one standard deviation, then you got something that looked relatively like this, and you started poking around and getting actual values. So you got the mean, you got the standard deviation, you were looking for the boundary markers. You did it again for 2 standard deviations and whatnot, but your teacher gave you a percentage value between the first set of standard deviations. Okay, that's 68, given. Between 2, 95. So once again, between one standard deviation is 68% of the curve. Between 2 standard deviations is approximately 95%. Still with me? I hope so. Now, normal distributions revolve around one equation and is the fundamental equation for statistics. And that is the data point minus the mean over the standard deviation. Take note that that little U symbol we're going to refer to as the mean throughout this course. And that little sigma symbol is also referred to as standard deviations. Now, technically speaking, there is another equation, and you could argue this completely, but they're relatively the same. You've still got a data point minus the mean over some standard deviation, where the x bar is also a mean value, and the s is also a standard deviation value. But the reason why that these two equations are completely different is because this one's dealing with populations while this one is dealing with samples. So are they really different in fundamental concept? Not really. The only difference between the two of these is how you find the standard deviation value. Later on, we're going to redefine this particular equation in another set of confidence intervals in another video. So for the moment, don't really worry about this particular equation. Focus more on this one. So a student asked me a while back, what does this have to do with normal distributions? I got news for them. It has to do with everything. The empirical rule is a fundamental rule that revolves around normal distributions. So if I take one of those items from the empirical rule, the mean plus 1 standard deviation, the mean minus 1 standard deviation, we refer to that total area as approximately 68%. But it also gives us 2 different boundary markers. Keep in mind that that boundary marker is a downward value, not a negative value. Doesn't have to be negative. Could be, but doesn't have to be. It's just down. And that 1 and -1, those are z-scores. So if we think back to the z-score equation, which is the data point minus the mean over the standard deviation, we have z-score equations again. And there is a way to bring this particular equation here back into this equation over here. Just replace the z with a plus or minus and you're good to go. For those of you who are algebra buffs, I will have another video to show this relationship. So my point, spoiler alert, if we took those same 2 equations, now that we know that the ones are z-scores, and we know that there's certain boundary markers, and we do it for the plus and minus. It does matter that we do the plus or minus for the spoiler alert. Well, if this contains 68% of the curve, well, wait a minute, between 2 values, approximately 68%, we could simplify this down to one equation. Because we have a plus or minus. So it's the mean plus or minus one standard deviation. Wait a minute. Those two values give us something we covered before. What was that? Confidence intervals. Yes, this is a variation on a confidence interval equation. So if a teacher came up to you and said, hey, calculate a confidence interval based on one standard deviation or 68% of the data, well, you don't need to go through your methods of finding a z-score because you already know what it is. So anytime that they say between two values, usually revolves around some idea of a confidence interval, which, again, you covered way back in the beginning. Spoilers. So, how important are the concepts of z-scores to students? Vary, because they have come up over and over and over again. Please don't ever lose sight of what a z-score really is. And personally, I've had students also ask me this: why should they care about z-scores? Got news for you. All items in statistics require a standard to work on. No statistician ever wants to work with summarizing raw data, incomplete data, or bad data. The standard for a given mean and population standard deviation, and if the distribution is normal or bell-shaped, then you have to deal with z-scores. So once again, if you are dealing with a population mean and you're dealing with a population standard deviation and the distribution is normal or bell-shaped, whichever you prefer, then you've got z-scores to deal with. Now in the next video, the actual next video we're doing, I'm going to go over the idea of the how to actually work with normal distributions, and then after that we're going to do the central limit theorem. So once again, thank you all very much for watching this video. Just remember, and this is the point of this video, if you have a mean and you have a sigma, emphasis on sigma, this thing, can't forget it, and the distribution is normal, then you have to deal with z-scores. This is very important for students that are taking their exams. So any questions? Nope? Well, if you do have any, please post them in the comments or feel free to email me. Thank you very much.